My name is Terrence Barkin. I'm the Executive Director of the Advanced Carbons Council, and together with the US Biochar Initiative, this is a joint presentation webinar on the topic of finding opportunities for biochar producers to identify value-added markets for their materials. You're going to hear first from Miles Gray, the Executive Director of the US Biochar Initiative. And with that, Miles, I'd like to hand over to you. It's all yours.
Great. Well, thank you, Terrence, and good morning, all. Before I jump in, I just want to say really appreciative of Terrence for pulling this together. And this kind of came together a couple months ago when Terrence reached out to me to talk about advanced carbons, and it really dovetails pretty well in our mission because USBI, we're really focused on the biochar side of things, and I'll get into what I mean by that. But having this opportunity for biochar producers to get into the advanced carbon space, it really works really well within our mission to support biochar producers. So with that, I will jump in. So US Biochar Initiative, we are a 501c3. We're focused on supporting the biochar industry broadly in the United States. We focus primarily on growing markets for biochar and developing standards. Our organization was founded in 2010. We host the annual North American Biochar Conference. Our last conference was in Minneapolis this past September. And we have funding primarily from the U.S. Forest Service and the U.S. Endowment for Forestry and Communities. And both of those organizations really support the wood products industry in the United States. And clearly biochar is an opportunity to add value to a lot of low value timber products. So that's really our mandate. And as I said, our approach to the biochar sector, first, we try to drive market adoption, primarily for the physical products. So we build and scale demand for physical biochar in agricultural markets, in the built environment space, in environmental markets as well. And we're really focused on those spaces where biochar is actively bought and sold. And we try to do everything in collaboration with the biochar sector. We're really trying to support the biochar industry to grow. And another thing we do is develop standards. And one key feature of the standards that we're working on, we're trying to develop standards for biochar in sectors where people would think they're using biochar. And what do I mean by that? Well, I mean things like agriculture, stormwater management, fertilizer products, maybe concrete, right? Spaces where a user, an end user might say, oh, that's biochar. So that's where we're trying to lead the development of standards because those standards don't currently exist in the market. In some of these other sectors, we're really just trying to support standards. And that, as I said, dovetails really well into the work of the Advanced Carbons Council because in this space, buyers aren't thinking they're buying biochar, they're buying different advanced carbon products. So in that context, we're trying to support the inclusion of biogenic materials into other standards. So that's really kind of how our standards work is moving forward. So now, what is biochar? One thing to know about this presentation, Terrence and I talked about this, and in some ways, what we're trying to do today is provide a background on biochar to the advanced carbon space and a background on advanced carbons to the biochar sector. So a lot of this will be repeat for some of you. Hopefully, you'll learn something from at least one of our slide decks. But I always start with the point that biochar right now, the term is used both for a material and a technology, and I'll dive into both. So the physical material, it's a whole lot like charcoal. It's essentially just a granular black carbon. The chemical structure of biochar is resistant to microbial decay, so the majority of the carbon is stable for at least 500 years or so, so long as you don't burn it. It can be made from essentially any biomass. As long as you're heating the material without oxygen, you can create char from essentially any type of biomass. The material properties of that material will depend on temperature and how you made it, and also the feedstock it's made from. But essentially any waste biomass will do, and it has multiple beneficial end uses. And just a brief kind of overview of some of the end uses that we tend to focus on, as I said, for like what people might consider to be biochar. A lot of them are in agriculture and soil. So there's a lot of interest in using biochar as a soil amendment to improve yield, water holding, soil carbon, and soil health. That's particularly true in some of the sandier soils. There's a lot of use of biochar in horticultural and potting media substrate. Similarly, can help plants grow. It can be used as a replacement for different products. There's increasing use of biochar in different materials in things like concrete and even in some composites and plastics and building materials. And then in the environmental space, there's growing interest as well using biochar in things like stormwater management and soil remediation. So these are a lot of the markets where you might consider biochar to be biochar, and that's where we spend a lot of our time. So in terms of the production technology, essentially biochar is a way to manage waste biomass that's pretty different from the typical management approach. So under the typical approach, you've got a pile of waste biomass, and it'll naturally decompose if left to its own devices. It'll naturally decompose over time, releasing CO2 and sometimes a little bit of methane back into the atmosphere. You can also combust that material and you can produce heat and power. This is really common in the wood products industry, taking a lot of these residuals and combusting them to produce electricity or heat. But essentially the same thing is happening to those carbon molecules. 90% of them emitted back to the atmosphere as CO2. Under the biochar approach, it's fundamentally different. So you're using pyrolysis or gasification, which is essentially heating that material greater than about 400 degrees Celsius in a limited oxygen environment. And when you do that, you convert about 20 to 25% of the biomass into biochar, but that ends up being more like 40 to 50% of the carbon because the final biochar product is enriched in carbon compared to the feedstock. The remainder of that ends up as these pyrolysis gases. So what do you get out of this process? You get some CO2, clearly. Some of that is being combusted. Those pyrolysis gases are typically combusted for heat or power. And then you get a whole bunch of biochar. And as I said, that's the goal of our organization, is really trying to support the development of markets and products using the physical biochar. So in terms of common feedstocks, there's a lot of different feedstocks people use in the biochar space. Wood and bark are very common. Agricultural wastes like rice hulls, construction debris, especially like pallets. There's a lot of pallets in the world. And the organic fraction of municipal solid waste, as I said, you can make biochar from essentially any biomass. It tends to be more suited towards drier types of biomass, but not exclusively. There are wet materials that are used in biochar production as well. Of course, in that case, you have to figure out how to drive off the moisture, either through some sort of pre-drying process or pressing, to squeeze that moisture out, or heat to get rid of that moisture. So that eats into some of the energy production from the biochar process. In terms of what biochar production actually looks like, and like the equipment that's used, right now we're seeing everything from mobile to industrial scale, and there's different reasons why you might go with mobile as compared to industrial. So on the left, some different mobile devices, the applied carbon unit, the Charboss and the Takachar, and this is not exhaustive by any stretch. There's many more types of devices than these. The mobile units, primarily, the premise there is that transporting feedstock is expensive. And so if you can move the production unit to the feedstock, you can, save a lot of money in transportation costs. And certainly true in certain contexts, that makes the most sense. As you move over to the right, there's some modular units like the Artichar units and the Pyreg units, and then bigger scale systems like Arex, Syncraft, ICM. Those are fully industrial systems processing in the tens of thousands of tons of biochar per year. Those tend to pair really well with locations where you've already got a whole bunch of waste biomass. So that might be at a sawmill or at a facility that recycles pallets, or an agricultural processing facility that, processes rice or oats or almond shells. So we're seeing everything across the spectrum. The industry is really growing right now, and the basic business model of a biochar company essentially is to convert feedstock into biochar, right? So you're starting with feedstock. It takes, as I said, about 4 to 5 tons of feedstock to produce a single ton of biochar. That's an important ratio to keep in your mind. So you're buying feedstock, you're using pyrolysis or gasification, and you're producing essentially 3 things typically. Pyrolysis gas, and that can be used for heat or electricity most commonly. Some companies are converting those py gases into fuels, chemicals, or hydrogen even. you can produce carbon credits, and these are pretty lucrative right now. And these are mostly being sold to different tech companies. They tend to be in the range of $100 to $400 per ton of biochar. And then biochar. And that physical product can range anywhere from about 50 to over $600 per ton of material, depending on the end use and the properties of the material. So one thing to go back to is that feedstock side. Right now, most companies are purchasing feedstock in the biochar sector, but there are opportunities to get it for free and even some opportunities to get paid to take feedstock. So we're seeing a lot of growth in that approach is can you make a tipping fee for using that feedstock? And there's more and more cases where that's true, particularly in the biosolid space and construction debris, municipal waste, things like that. One thing to know about these carbon credits is they do not permit uses where incineration is a possible end of life. I mean, clearly the whole point of the carbon removal credit is you're converting a labile form of carbon in waste biomass into a sequestered form of carbon in biochar. But if you burn it, or if there's any risk of it being combusted at the end of the process, that undermines the legitimacy of those carbon removal credits. So that's obviously a super fast overview of what companies are doing in the biochar space, but that tends to be how I think of the business models of biochar. So now I'm going to pivot a little bit from that sort of high-level overview of the biochar sector to a little bit around how biochars might be used as precursors for advanced carbons. And clearly, I'm not an expert in advanced carbons, but I'm decently knowledgeable about biochar as a physical product. And so I'll dive into sort of four key factors that might play into the use of biochar in advanced carbons. And those are going to be carbon form and degree of aromaticity, porosity and surface area, ash, fixed carbon and volatile matter, and initial surface chemistry. And in many ways, these four things are really controlled by feedstock and production temperature. On the right, I've got some figures that I got back when I was a wee youngin in grad school. Of Douglas fir and hazelnut biochars. And so you can see that impact of feedstock and production temperature right in those images, right? You can see that the production temperature changes, particularly in the Douglas fir. You can see that it's going from thicker cell walls there to much, much thinner cell walls. And then obviously there's an enormous difference based on feedstock. So in terms of carbon form and aromaticity, essentially at lower temperatures, biochar production between about 400 and 800 degrees C, you're getting these turbostratic graphitic sheets. They're not graphite by any stretch, but you're getting some of those properties. So you're getting these small sheets that are sort of disorganized. And as you increase production temperatures, you get more organized graphene sheets until eventually you get to graphite materials. But it's important to know that biochar is far, far from that sort of like fully graphitized production temperature. And that's really important here because like the way that biochar might feed into an advanced carbon process would probably be as a feedstock that would then be heated to much higher temperatures to create graphite or other advanced carbon products. So biochar is getting a little bit of the way there, but there's a lot more work to do to get it to those advanced carbon products. Porosity is also really important. I tend to think about biochar pores in three buckets. First off are just these external pores. If you have a pile of biochar material, external pores are just the pores between particles. It's no different than a pile of sand, right? The size and the shape of those pores is really just dependent on the size and the shape of the particles themselves. Then there's two types of internal pores. So there's these internal macropores, and these are the larger internal pores that are dependent on the cellular structure of the feedstock. So in this Douglas fir biochar, this wood biochar, you can see that those are preserved from the cellular structure. In wood, they tend to be about 10 to 60 microns in diameter. And those contain the majority of the internal porosity of a biochar material. Now, at higher production temperatures, you can get these internal micropores, and I don't have a picture because they're so small that you can't actually see them. So there's no image there, and they tend to be in the nanometer range. They contain only a small amount of the total pore volume, but they contain the majority of the surface area. And so you can see that pretty clearly when you look at surface area. And so this is some idealized data for surface area of biochar versus production temperature for a couple different feedstocks. And so as you can see, that surface area increases with temperature due to the production of these nanopores. These internal micropores are forming due to the reorganization of carbon. And again, really dependent on production temperature and feedstock, with wood and nutshells tending to have higher surface areas, and grass and biocell tend to be lower. You see a lot of that increase in surface area right around kind of the 400 to 600 degrees Celsius range. Above that, it tends to level out. Um, Obviously, for things like activated carbons, you can increase that surface area with different activation technologies and techniques. But biochar tends to level out once you get to about 600 or 700 degrees Celsius. You don't get a whole lot more in terms of surface area. You do continue that graphitization process. Um, but again, to get to those higher end products, you're needing to get much higher temperatures than is typical in biochar production. So now fixed carbon, ash, and volatile matter. The general story here is that fixed carbon and ash tend to increase at the expense of volatile matter at increasing production temperature. Um, and these are methodologically designated properties. These aren't like real things per se. Ash is essentially the material left over when you fully combust a sample of biomass. Fixed carbon is the amount that doesn't volatilize at 900 degrees Celsius, and then volatile matter is that portion that does. But you can see pretty clearly that ash content goes up for all of the biochar materials. It doesn't go up that much for wood and nutshells. That's partially because they just don't contain a whole lot of mineral content to begin with, because that's primarily what the ash is composed of, are different minerals in that biomass, which is primarily composed of carbon, hydrogen, and oxygen. Fixed carbon also increases, and that's sort of the more stable portion of the carbon. And then volatile matter, which is that portion that volatilizes, clearly goes down with increasing production temperature. And these are all important factors. These three properties are frequently used sort of as a rapid analysis of biochar, or a really high level understanding of what biochar is. And then finally, initial surface chemistries. So biochar is essentially composed of these graphene sheets, particularly once you get above 500 or 600 degrees Celsius. But then on the edges of these sheets, you get a whole lot of surface functionality. Different types of functional groups are present on the edges of these graphene sheets. In general, those tend to disappear at higher production temperatures. As I said before, a lot of these end up volatilizing as volatile matter, right? So when you get to those higher production temperatures, you don't have a whole lot of these surface functional groups or surface functionality, but you can add a lot of this back in via activation, and actually even via environmental aging. When biochar is exposed to microbes in the environment, it builds a lot of this back onto the product. So super quick overview of some of the features that are probably going to be important in using biochar as a precursor for activated carbon or advanced carbons. And just real summary, I think there's certainly biochars out there that are likely candidates as advanced carbon precursors. Higher temperature biochars are likely going to be among the most suitable. And one of the things that will have to be dealt with is ash, particularly for some of these higher value products. And another piece here is I think this specific upgrading processes will likely be developed for any given advanced carbon product. So I spoke a little bit about feedstock and purchasing feedstock versus getting paid to take it. And a lot of times companies that are generating revenue by taking feedstock are probably taking a little bit of a diverse incoming stream of material. That probably won't work all that well in the advanced carbon space unless you have some real consistent feedstocks. That's probably going to be a really key feature, is consistency in feedstock and production conditions. And that will work for certain feedstocks and for certain production methodologies, but it certainly won't work for all biochar producers. So with that, I'm going to hand things over to Terrence.
Well, thank you, Miles. Appreciate that. I will go ahead and do my presentation now, and then we'll have a Q&A session. We already have a number of questions coming in. Okay, so biochar opportunities in the advanced carbon space. If you're not familiar with who the Advanced Carbons Council is, we are an international trade association that focuses on the full spectrum of advanced carbon materials. We started in August 2013 as the Graphene Council. That was our core and our initial start, but we now cover a much broader range of carbon material. When we talk about advanced carbon materials, we're talking about things like graphene, carbon nanotubes, carbon composites, and even macro materials like carbon fiber or reclaimed carbon fiber. Biomass and recycled or reclaimed carbon would cover the biochar materials. So we cover this full spectrum, and we focus on the commercialization and application of these materials in different applications. So the question for our presentation today is, what are the opportunities for higher value add products for the biochar producers? We want to look at things like using more refined biochar materials directly in construction or those kind of applications. They can be converted or graphitized into graphene carbons, carbon nanotubes, or things like hard carbons that can be used in battery. We do have a number of graphene producing companies within the Advanced Carbons Council that are using biochar as a precursor, and then they're further processing that to make either graphene or carbon nanotube materials. And synthetic graphite is another opportunity. The big challenge that we see, frankly, in this is for biochar producers often don't have access to the type of equipment that would be needed to graphitize this material, which is more at 2,500 to 3,000 degrees centigrade versus the temperatures that you're typically processing biochar at. And then beyond that, once you've made these advanced carbon materials, is to find the applications in the downstream products. So if we look at the value chain for advanced carbons, we can start with raw materials. So this is kind of any kind of carbon bearing source, which in the case of biochar, you have biomass materials. But in the case of graphene or advanced carbons, this includes carbon bearing gases and even recycled plastics or any kind of high carbon content material to be considered a raw material. And I think for our conversation and for this community, we're talking about the production side. So you might be taking a biomass and converting it into a value-added carbon form, and that could be your biochar, or with further processing, as we've seen with graphene or some of the other advanced carbons, using the biochar as the raw material per se, and then graphitizing it, and then micronizing or getting it down to the atomic level or the nanoscale to turn it into some of these advanced carbons. There is going to be another phase of work that needs to be done in post-production, and that could be separation technology. So as Miles referred to with biochar, you may have a certain proportion of ash or unwanted components into the materials that need to be separated out. You may also have to do post-production processing to eliminate the larger scale, larger size primary particles from the smaller scale particles. Functionalization is the intentional addition of additional chemicals or elements to the material to improve its performance. So you might have a phase where you actually add oxygen groups or you add some other chemical groups for a certain performance factor. And then there's also formulation. In the carbon nanotube and the graphene space, for example, rather than have customers use the nanomaterials directly, these might be put into a master batch formulation combined with, let's say, a thermoplastic as a master batch additive like polypropylene or nylon, a PA material. And that's what is sold on to the customer. And then as you move further, then you have the end uses. And that's really, I think, where the Advanced Carbons Council plays a role in this particular discussion for biochar producers is what markets is your material ultimately going to end up in? And this is where we need to stimulate demand in order to create a commercial market for any of these materials. So does it end up in transportation, automotive composites, concrete, asphalt, paints and coatings? where is the material ultimately going to end up? And it's important for people earlier in the supply chain to understand what the end use markets are for several reasons. One is to understand what kind of an advanced carbon material makes the most sense for you to focus on trying to produce. And secondly, making sure that you're producing it according to the specifications and at commercial terms that are going to be acceptable to the end use markets. And so, what we try to do as an association is to help educate all of our stakeholders. That means producers and the end users about what these materials can do and how to apply them. From a commercialization strategy, you'll have companies that are more vertically integrated. So they might own a supply. This could be, let's say, a natural graphite mine, for example, and then produce carbon nanotubes or graphene from that. And then they functionalize it, put it into a formulation, and sell it on. And they would control all of those components in a more vertical integration. Or we have companies that just focus on the post-production manipulation of the materials, for example. So it's also trying to understand where you might fit in that value chain. If we look at graphene and what it is, graphene was only unveiled or discovered in 2004. The Nobel Prize in Physics was awarded for that discovery in 2010. So this material has only been around for about 20 years from discovery. So it's quite young by material standards. And typically, over the history of, if you're looking at glass or aluminum, or you're looking at fiber optic cable or whatever, when a new material is discovered, it usually takes about 30 years for it to be fully commercialized. And where we're at with graphene is we are in the commercialization phase. So we have adoption of graphene now in many, many different applications. So graphene is not one material, but it's actually more like a family of materials. And what you see here, the four images on the left are different types and forms of a graphene material. And the one on the far right is more of an amorphous carbon. You could think of things like carbon black. And with biochar materials, what we have seen, what this is a relatively new material for us, but what we have seen is often there's a combination of sp2 bonded carbon and amorphous carbon in the mix. And so the question then becomes, do you need to work on separation technology or further processing, or do you tweak your production processes to gear more towards more sp2 hybridization of the carbon to get the end product? So those are just some considerations there. If we look at carbon nanotubes are 10 years older than graphene, and we see it's a more mature market. There's about 125 companies that we've identified that are active in the carbon nanotube market. And carbon nanotubes have established themselves as a very well-used material in the battery sector. And of course, batteries is a rapidly growing market segment at the moment. And so they've kind of found their niche. One of the end use markets for biochar potentially is as a hard carbon. And I don't have a slide up for hard carbons, but hard carbons are an ideal material for sodium ion batteries, for example. So that might be a nice niche application, or as synthetic graphite. So if we look at the size of the markets, carbon nanotubes at 30 years old is a much more mature market than graphene, and it's a very large addressable market, primarily in energy storage, electronics, and this is one of the areas with the advanced carbons is either being used for their high electrical conductivity or for their high thermal conductivity, or both, lends them to certain applications. So there's a lot of markets to look at. So pathways for value add for the biochar market could be in improving existing materials. And we've seen, for example, biochar being used as an additive in asphalt. And we've done testing with graphene, carbon nanotubes, and other allotropes of carbon in asphalt. It's a very large market, very price sensitive, but there's opportunity there to make asphalt that is more temperature resilient, longer wearing, so that the roads don't need to be replaced as often. For example, the same with concrete or some other applications. And then the other thing to think about is engineering some of your biochar and making it more reproducible, higher carbon content, less variability, certain particular particle morphology, and identifying key markets where that are especially price sensitive because biochar can be produced at a pretty efficient price point, and look at markets just for the biochar material itself. So Miles mentioned briefly standards. There are obviously well-established standards for biochar, primarily for the agricultural use. So it focuses on its attributes in that application. Where there are not good standards at the moment is on the non-agricultural application type use. There is a specific standard being produced at the moment for biochar in cement and concrete, but not for other non-ag uses. And that's an area where I could see USBI and the Advanced Carbon Council collaborating on is the establishment and definition of those standards. If the biochar community wants to sell its materials into a supply chain that is going to further process these materials, let's say for synthetic graphite, in battery materials as coatings, or in some other application, there is going to be a need for well-defined quality standards for those materials, how to test it, which characteristics, and to make sure that it's consistent if it's ever going to be accepted as into the supply chain for advanced carbons. And this is an open invitation for any and all stakeholders in the sector that if you would like to be involved in the development of those standards, and I would encourage you to do so, even if you don't think you can contribute to the writing of them, to at the very least share your concerns and to stay aware of how these standards are being developed. We do have a volunteer task force for biochar standards for non-agricultural applications, and we're more than happy to have your involvement in that. So cost is always an issue. I think there's an advantage for biochar, the biochar community with advanced carbons, because as Miles did point out, and I thought the presentation was excellent, there are elements, and we're well aware of these, where a biochar producer can actually be paid for taking some of this material off of a supplier's hands, like municipal waste, for example, is a really good example for that, in converting that material. If you are going to get into the field where you're producing a nano material, at least in the United States and Europe, there are regulations, TSCA, for example, managed by EPA, that regulate nanomaterials and treat it as a chemical. And so there do need to be approvals for nanoscale materials if they're sold as such. Life cycle analysis needs to be done. We've just completed a product category rule exercise for graphene so that we can calculate the life cycle assessment for the production of graphene and issue an EPD, or an environmental product declaration. And we do have quite a large community within the Advanced Carbons Council. Like I said, 40,000 materials professionals that we reach. And it'll be important for us to educate these potential end users about biochar. For many of them, they don't really know what biochar is. They won't appreciate the differences between material that's produced from different feedstock, how it's processed, and what it can be turned into. And then I think the biggest challenge, quite honestly, for the biochar sector is going to be consistency in producing a product that has the same kind of carbon output and the same quality and the same chemical composition on a repeatable basis. And so I think that's where biochar producers that work with a consistent species or biomass input, and they have good quality control on their production processes, are going to have an advantage. So that's something to think about. We are actively looking at how we can explore what markets biochar can address. And with that, we encourage engagement with USBI as an organization and with individual biochar companies that want to focus on this value add journey. We quite honestly believe that there will be a very small segment of the biochar production community that will have the capital processing capability, equipment, vision, and everything else to address these markets. And that's not to make a qualitative judgment on it. It's simply that the bar is going to be a little bit higher to reach an advanced carbons market than it is, say, for biochar for some of the well-established markets like agricultural and soil amendment. And again, that's not a judgment, that's just an observation that if companies do want to address this market, there are some technical obstacles and processing obstacles to be addressed in order to reach it. The flip side is, as a higher value add carbon, there is a price premium and a higher cost or a higher sellable price that can be obtained, and that is the attractive part of it. And that's really the objective: is how do we turn this into a business where you can get a higher margin for your materials because they're engineered to a higher specificity for a higher value add end use. So that's the role that we play, is to kind of help companies along that journey, how to identify those markets, how do we address the technical issues, and how do we connect you with potential customers for those products. We encourage companies to think about joining us as a trade association. I really want to salute Miles because not many associations have the vision of a surplus mentality. Many people look at this as a zero-sum game. If you're a member of one organization, you can't be a member of mine. There is no law that says you can't belong to more than one association at a time. We see these as complementary. And so if you think we can address some of your issues, we encourage you to engage with us. And we certainly encourage every biochar company out there to be engaged with the US Biochar Initiative, because we think they're doing absolutely great work and have great leadership in this field. And so it's a case of 1 + 1 hopefully equals 3. So with that, those are my contact details. I'm going to stop sharing my screen and we're going to go to Q&A. If I can figure out how to do that. There we go. So thank you for your time and attention for that. And now with that, Miles, let's see what kind of questions we have. And let me just do it this way. There we go. So we're on equal footing.
Yeah, one that maybe I'll take, Terrence, and actually they were two. They came in early in the presentation from Liberty Gura and Randy Latoon. They were both related to whether or not essentially chars made from plastics or from natural gas pyrolysis, and I'll just kind of lump them together, would be accepted for agricultural purposes. And I would say that right now, they wouldn't probably be considered biochar, right? Because the bio part generally requires that they're derived from non-fossil sources. That's the starting point. But then whether they'd be approved for agricultural purposes, I would say, I think certainly possible that, particularly in the fertilizer space, there could be applications where those types of chars would provide a lot of value to fertilizer products, particularly if you can increase primarily nitrogen use efficiency, which is a big goal of the fertilizer industry around the world, really, is to increase use efficiency from what is typical, which is about 50% of nitrogen ends up in a plant. If you can increase that value, there's some real benefit. So that's one that I can answer.
Excellent. Well, I think this is a really good example, Miles, of where the continuum of materials is important. We do have companies that are looking at recycling plastic materials and turning them into value-added carbons, and that be that the carbon nanotubes or graphene, for example. So I think the approach we want to take, and maybe the message we want to this audience, is engage with us directly, ask us about what your process is and what you're able to produce, and then we can talk to you about, okay, where does that fit in the panorama of these additional materials, and then which markets are the most applicable for that. I think that's probably the best way to look at it. Miles, did you see another question you want to take?
I saw one for you that I was really interested in from Tony Marrero, which is, what are the materials that biochar-based advanced carbon replacing, and what is the annual total market potential by tonnage? That's a question I've kind of been ringing around in my head. Is like, what does the size of this market look like in tonnage, not necessarily dollars?
Yeah, so that's a really interesting one. So we looked at, so obviously our biggest experience is kind of with graphene, but to give you an example of looking at graphene in just the concrete market. So 1/10 of 1% of the global concrete market for graphene, and graphene is added at hundredths or tenths of a percent by weight into concrete. So a very, very small amount. 1/10 of 1% of that global market is 110,000 metric tons. Okay, so that's just one small market. So we're estimating between 3 to 500,000 metric tons of graphene, which is used at tenths of a percent, extremely low load factor. If you're looking at biochar directly into asphalt, and maybe now you're talking about 3% by weight, then you're in the hundreds of thousands to potentially millions of tons of material that are required to be added in. And it's kind of a scale. We have graphene materials that can be sold and used into thermoplastics, and the price point could be as high as let's say $1,000 a kilo. Typically, it's a kilo, right? So that's 100,000 a ton, which obviously is quite interesting, but it takes a lot to get to that point. And then when you're using it, though, you're using tenths or thousands of a percent by weight. So it's a very, very small amount of material. So that's kind of the juxtaposition, very high price, small volume. And somewhere along that spectrum is where you want to find the sweet spot for your material. I don't know if I've answered your question, but elastomers, coatings, plastics, all of those are somewhere at 100,000 metric tons per market.
Mm.
So what was the other part of that question?
Oh, I think you got it. It was talking about the total market potential by tonnage.
Okay. Okay.
And I think it was a good question because a lot of times in the biochar space, certain higher value markets are much smaller in tonnage, higher in value, smaller in tonnage. This could be a similar situation, right? Clearly.
Yeah.
Um,
So there's a question, or maybe this one's for you. If you can separate cellulose from the biomass in agricultural waste, can you use the lignin and carbonize it? And is this the same for biochar? This comes from the coconut group, so I assume this has to do with coconut fibers.
yeah, I'm certain that you can, I'll be the first to admit I am not an expert in biochar production. Clearly, I know a decent amount about it, having been around this space for a while. I know groups have done work in that space, and I also know that groups have been able to make some like sort of naturally nano biochar by using the lignin component only. Um, but honestly, to me, it appears that a lot of that information is protected by different IP. It's some of it gets published, some of it doesn't. So that's probably the best answer I can really provide at this point, is that yes, it can be done, but I'm not sure how and what it ends up with.
Well, the question from Brian Berry is like, what raw materials currently feeding the advanced carbon production, and what advantage does biochar have for advanced carbons over other carbon resources? I think that's a really appropriate question for what we're talking about today. So the first part of that is what carbons are being used. So traditionally, graphite is used as a precursor material for a lot of graphene production, but any carbon bearing source, so methane gas, acetylene, ethylene, these have all been used to produce graphene. Graphene's being produced, and other nanocarbons are being produced from recycled plastic materials and from biomass materials. So any highly carbon rich material can be converted and graphitized and made into these sp2 bonded carbons. Then what's the advantage of biochar? Biochar, if I look at raw graphite flake, you're somewhere around $1,200, $1,500 a ton for raw material cost. Biochar is, if I remember the slide correctly, you're, around $100 to $400 a ton, somewhere in that range. And you also have the carbon credit aspect of fixing the carbon. So that adds into the value chain of this. So those are some advantages. I would say the biggest challenge is, can you produce the same kind of carbon material consistently in terms of chemical composition and physical morphology of the particles on Monday, on Friday, a month from now, and 6 months from now? Can you do that consistently? And so that comes down to process controls and post-production processing. I think that's the biggest challenge. So the upside is biochar potentially is a low cost source of the raw carbon material. And the challenge is going to be whenever you're dealing with a biological or a biomass input, you get variability. And that's going to be, I think, the challenge. I don't know, Miles, if you have a comment on that one.
I think that's true too, and I think one of the challenges is both can you get the exact same feedstock, but also moisture content of feedstock can vary day to day. You see that in the wood sector and any other biomass source. It even varies based on the relative humidity outside. So whether or not you can make that get those drying conditions right and the same very consistent feedstock. Which is why I think in some ways it points to facilities that are co-located with like a sawmill potentially, right, where you're getting the exact same nice sawdust on a daily basis, or a oat hull mill or something like that, right, where you're getting a very consistent. It's also possible you could see it in the biosolid space too, because that material tends to be pretty consistent as well. Going to be a little higher ash though, so.
Yep. Well, and that's not always a bad thing, right? Ash isn't necessarily always a negative. It's just it may just limit where the end use is. The other thing to consider is some end use applications, like asphalt, for example, are much more tolerant for variability.
Mhm.
If you're going into the battery space, you have very close tolerances and no margin for impurities, right? Or trace metallics or something like that. So the battery market might be much more difficult to access, whereas something like concrete and asphalt will allow for more variability in the material and tolerances. So it's again matching. We've kind of said this from the beginning. There's no such thing as a good material and a bad material. It's more about what is the best use application for the material you're producing, and finding that fit. Um,
Terrence, I have one that's related to ash in here that was put in here relatively early, is whether or not the ash poses a challenge when using biochar in different applications, and the follow-up is can it harm soil health and how can this be addressed? I would say in general, ash is not an obstacle to using biochar in agricultural applications. It depends on how you're using it, but as a soil amendment, ash is actually pretty beneficial in many cases. It contains a lot of micronutrients. It also typically provides liming, which most soils are acidic and need to be limed. And even those soils that aren't naturally acidic tend to become acidic as a result of synthetic fertilizer use, right? Which is ubiquitous and critical. So no, ash is not an obstacle to using biochar in agricultural situations. It might be a little bit more of a challenge in using biochar as a fertilizer input, but certainly not as a soil amendment.
Excellent. The last question I see here from Shintu, which we appreciate, in what ways can research institutions partner with the Advanced Carbon Council to accelerate innovation, testing, commercialization of advanced large-scale carbon materials from algae? So that's quite specific. And I would say that applies to basically any process that you want in looking at these advanced carbons. So we run the full spectrum from working on standards for classification and definition. We also provide material testing and characterization services, so we can actually, to a very specific degree, analyze the material and then categorize it and see how it compares to the spectrum of other advanced carbons. So where does it fit in that comparison? And then one of the other things we do as an organization is actually application testing. So, for example, we test these advanced carbons in thermoplastics or coatings or composites and do the physical testing to see if they actually are effective. And that data then in turn is disseminated so it helps stimulate demand and help educate customers on how these materials perform. So we can work with you on any point along that spectrum, from production processes, scaling, testing, and characterization of the material, and even on the regulatory approval side, if that is applicable. So the easiest thing is have a conversation with us, engage with us. We do a lot of work. I would say 90% of what we do is under NDA because people are developing innovative product and applications. And so we can, we're quite sensitive to intellectual property protection and that sort of thing. So yeah, I hope I answered that question.
Yeah, there's another one that just came in that I'll take. Is there any structural difference between the biochar extruded from various sources? And I would say within the biochar range, there certainly is. It's noticeable. A wood biochar or a nutshell biochar is certainly much harder physically than a oat hull biochar. So the hardness of the initial feedstock certainly is carried through to biochar production temperatures. I'm not totally sure what happens at those much higher temperatures, but in the biochar range of kind of 400 to 800 C, yes, the physical properties of the incoming biomass are translated into biochar. Of course, everything becomes more friable in biochar than the original feedstock, but and actually, you see this in the activated carbon space. One of the common activated carbon precursors is coconut shell biochar, essentially. But you wouldn't typically use, at least for a granular activated carbon, you wouldn't typically use a straw biochar, for instance, like a wheat straw biochar, because it tends to be too friable as a granular activated carbon. So,
Excellent. So I have a question for you, Miles. Would you say that most biochar producers have a really good granular understanding of the material they produce? I mean, at the chemical level and that sort of thing. I mean, how much analysis is done? Because for the advanced carbon space, the chemical composition, for example, is extremely important. I mean, that's basically the majority of the focus is what is the degree of carbon content and what form of carbon is it? Is it amorphous or is it an sp2 hybridized version of carbon?
I would say right now, most biochar producers have more bulk analyses. So things like proximate analysis, ash, fixed carbon, volatile matter, surface area, ultimate analysis of different atomic ratios, things like that. And it's actually something we've been working on quite a bit is an updated ANSI standard for the analysis of biochar. That primarily contains analyses, as I just mentioned, which are more ultimate and proximate analyses rather than any of these more advanced analyses. Like there aren't a whole bunch of aromaticity measurements, right? Or sort of there's no tests for sp2 bonding in biochars right now. You could include them, I'm sure, but we haven't included any of those because in those biochar applications, they tend to be a little less important, right? In the true sort of true biochar applications.
Right. No, that's what I understand. I think that's maybe another distinction that the community should be aware of, right? Because
Mhm.
as you go up the value chain for this, the chemical composition, and there is a question here, some from Saraswati, is what is the ideal chemical composition of a biochar? And in the advanced carbon space, the goal is almost always ultimately pure carbon, right? And that doesn't mean defect free because the defects sometimes can be actually quite advantageous. But from the chemical composition, normally we're looking at as high a carbon content as possible is the ideal.
Mhm.
Having said that, there might be some other elements in there that are also advantageous for a given application. So it's not a rule that only pure carbon is what is needed. But if you don't have a high degree of carbon content, then it's probably a less desirable product.
Yeah, and in the biochar space, I would say that's not typically true for certain applications. Yes, you're going to want a high carbon product like filtration applications for water filtration. But for soil amendment, as I said, ash can be beneficial. And then for other uses, right now, we're seeing a lot of interest in using biochar in concrete. And part of the benefit there in concrete is actually the ability to use biochar, the minerals, the ash content, to provide essentially a replacement for they call it supplemental cementitious materials, SCMs.
Yep.
So there's some benefit there to the ash content is really providing that cementitious property in the concrete space. So it just depends on your end use.
I think that's a great example. So we're quite agnostic from our side. Obviously, we're focused on advanced carbons. That's kind of the focal point. But at the end of the day, you have biochar producers. You're producing a product. You need to find an offtake market for that. It needs to go somewhere that's commercially viable. There are many options for that, and that's kind of what we want to explore with this. Miles, if you're okay, if you have any last comments, I think maybe we'll conclude today's webinar.
Yep.
And yeah, what would you like to leave us with?
Just really appreciate you reaching out, Terrence. And our goal as an organization at USBI, we're trying to help biochar producers find markets, and to the extent that that is in the advanced carbon space, we're happy to help and happy to participate how we can.
Thank you for that. Likewise, I really appreciate your approach. I also want to commend you. I think you've done a fantastic job with USBI, and I was very impressed at the conference in Minneapolis. It was very professional, and there's a real buzz for your industry. I'm excited for you, and I'm excited for the biochar sector. If we can play a very small role in helping a few folks, find other offtake markets for their material, that's what we'd love to do. And so on behalf of the Advanced Carbon Council, thank you, USBI, and thank you for everybody who's joined us today. We appreciate your time and attention, and reach out if we can be of further help. Thank you very much.
Great. Thank you.
Take care.